Good afternoon. My name, as you heard, is Kathrin Altwegg. I'm a professor emerita from the University of Bern. I studied solid-state physics, made a postdoc in physical chemistry, and then ended up by chance in space research. So I changed the field several times, which actually is quite good, because it gives me more experience, and I need that for comets. Comets, origin and composition, this title was given by Hervé. If you read papers on comet composition, one of the first sentences you read is always, comets contain the best preserved material in the solar system. And I will show you that this is probably right, even if it's copy-paste from one paper to the next, but it's still probably right. On the other hand, comets are big imposters. That's a comet, no doubt it's Comet Halley. But actually the comet, that's this here. It's a very tiny nucleus, a few kilometers in size, and it makes a big noise. So if you think about comets, you normally think about this, but actually that's the comet. It's small and it's pitch black. It's not white. We will come to that. So we start with the origin of comets. Where do they come from? You probably know that we have two distinct families of comets, the Oort cloud comets and the Jupiter family comets. But actually, that's where they reside now, not where their origin is. That's the solar system. You see the planets, and then outside of Neptune, you see the Kuiper belt and the scattered disk, and then starts the Oort cloud. And the Oort cloud starts to become spherical around the whole solar system around at 5,000 astronomical units. Here you see the temperature. If you are in the scattered disk, you are already down at roughly 10 K. So it's really cold out there. Now, where do comets reside? That's an animation over the 100 years. Only the innermost orbit is Jupiter, not Mercury, it's Jupiter. It's the big planets. The blue ones are comets. And you see they go inwards and then outwards again. That's just how this is calculated. Of course, you have new comets coming inward and going outward. The solid squares are Jupiter family comets. They don't go out, they don't come in, they are always there. And then we have the centaurs, these triangles here, and Plutinos, they are in resonance with Neptune, and then the TNOs, trans-Neptunian objects, and the scattered disk objects further out. That's how the outer solar system looks like. Now, how do we know that? Because we cannot observe the Oort cloud. It's too far away. The Kuiper disk, we can observe the big objects like Sedna, but not the comets. If you compare sizes, we have the Earth, Pluto and Sedna have about the same size here. And if you look at the distance from the Sun, you have Pluto here, and the Sedna is 3 times further out. So it's huge. It's much more than what we normally think about the solar system. But if you now calculate backward from the comets you see, backward to where they originate, you get the Oort cloud spike. And the spike looks like this. The binding energy of a body is proportional to 1 over its semi-major axis. And that's a binding energy. If you plot the binding energy versus the number of observed comets, you see they have a big spike very close to zero. Binding energy almost being zero. So just barely bound to the solar system. If you enlarge this, then the peak is broader. We have here fake, false hyperbolic comets. They are probably not real, but you see the peak, and the maximum here is below 0.0001. And if you now invert that, that means above 10,000 astronomical units. So these comets come from further out than 10,000 astronomical units. And that's the active Oort cloud. There is also an inner Oort cloud, but comets from the inner Oort cloud do not come back because they don't get the gravitational pushes as the outer Oort cloud. So that's the inner Oort cloud here, and then above 10 to the 4, you have the outer Oort cloud. And that brings us to the question, where is actually the edge of the solar system? And here with edge, I mean the gravitational conditions, that the bodies are still bound to the sun. And that's even much further out. It's at 350 kilo astronomical units, if you calculate that. Now, how did the solar system evolve? You start out with a disk. The dust falls down to the midplane, so the midplane is full of dust. It's dark, intransparent here, and that's where the planetesimals form, the small bodies. Then the planets form, they clear up their orbits, so no more dust in their orbits, no more planetesimals in their orbit. They are cleared away, and then the interplanetary region clears. The Kuiper belt evolves, I will come back to that, and the inner and outer Oort cloud form. That's how we think the solar system emerged. The Oort cloud formed because of the big planets. We have a lot of small planetesimals close to the big planets in the beginning. And if they are scattered by the big planets, that's a little bit like space ball here. The small planet comes, Jupiter comes much faster with about 50 miles per hour, and then the small body is ejected up to 130 miles per hour. And that means the planet ping pong, what it can do, it can change the semi-major axis, it can push the small bodies out, but it cannot change the perihelion distance, this here. So that's A minus C. And it can only marginally change the inclination to the ecliptic. So these bodies go out, have a big semi-major axis, but still a small perihelion, a very eccentric ellipse. The potential energy, as I already said, it goes with 1 over A, and if a small body encounters Jupiter, that's it. It's lost. Also with Saturn, they are too big. So they get too much energy from the big planets and they disappear. What makes the Oort cloud is then far encounters with Saturn, if the body does not get too close to Saturn, or close encounters with Uranus and Neptune. And you see here, Neptune mostly populates the inner Oort cloud, and Uranus, together with Saturn, the outer Oort cloud. So these were bodies formed in the vicinity of Saturn and Uranus, but never had a close encounter with Saturn. Now once they have a large semi-major axis out in the Oort cloud, the small bodies start to feel the galaxy. Our sun is somewhere here. It's not in the center of the galaxy, fortunately, but it's also not at the edge of the galaxy. And the galaxy rotates, and with the galaxy also our sun, our solar system, and this leads to tidal forces. We normally associate tidal forces with the moon, but you have the same effect here with the galaxy. The tidal forces of the galaxy, they play a role because the solar system plane, the ecliptic, has an angle of 60 degrees versus the galaxy. And so if the galaxy moves, we get tidal forces once in this direction and then a little bit later in the other direction. So it's like tidal forces on the Earth. Now tidal forces, they can increase the eccentricity, which then would actually push the comet back into the inner solar system. But they can also increase the perihelion. And once the perihelion gets large enough, this body is captured in the Oort cloud, if the perihelion distance is equal to the semi-major axis. Then it's a circle. They can also change a prograde orbit into a retrograde orbit of a comet. Another mechanism out there, once the body has a semi-major axis which is far out, is encounters with stars. If you have a solar mass star in the distance of 0.5 parsec, then you get the delta V, velocity change of 20 kilometers per second, and that will change the orbit of the small body. And we do have some stars in the vicinity, not that close, except this here will be closer in 1300 years to us, and that's the past. There was not really a star very close to the solar system. And the third mechanism is an encounter with a giant molecular cloud. Molecular clouds are very massive, they have a lot of mass. If you encounter such a cloud in some distance, again you will change the orbits of the comets in the Oort cloud, because that's the furthest from the sun. They are least bound of all objects. And here that's an example, it's a model. What happens in the beginning, you have a perihelion distance close to Neptune. Then you encounter Neptune, your semi-major axis increases very fast, and then the perihelion distance increases more slowly due to the tidal forces. And then you may have some stellar encounters which also change the inclination of your small body. And in the end, you end up with a spherical Oort cloud all around our solar system. And that's an animation. We start with small bodies near Jupiter, Saturn, Uranus and Neptune, and in the Kuiper belt, and we'll let it run. You see already after 1 million years, the semi-major axis has changed, except for the ones for Neptune and the Kuiper belt. But the perihelion distance is still about the same, because they have not yet reached where the tidal force works. But then it goes pretty fast and you form your Oort cloud. And in the end, you still have some of the Neptune comets here, but part of them are also in the Oort cloud. And the same for the inclination. You start at 0 inclination towards the ecliptic plane. After 1 million years, you have enhanced inclination, but moderately, but then it really starts. And you form this oil cloud. And how do they come then back? Not all of them come back, but a few. We see them every year. It's the same mechanism. It's tidal forces of the galaxy which can push them back, and it's disturbances by stars and molecular clouds, gravitational perturbations which push them back into the inner solar system. Now the comets from out there, they have one problem, and that's Jupiter. If they want to come inside of Jupiter, they have to do that very fast in order not to meet Jupiter on the way. And that's the so-called slope due to the barrier of Jupiter. So you have the Oort spike. Only comets which come from very far out will be able to cross Jupiter without encountering the planet in one go. And that means they have to start at 20,000 astronomical units. Let's come to the Kuiper belt. Kuiper belt, we know that we have a Kuiper belt, but the other solar systems also have Kuiper belts. These are exoplanets here, or exo-Kuiper belts, whatever you call them. Around the sun there are extended ones and narrow ones, and we have a relatively narrow one in our solar system. The Kuiper belt evolved from the migration of the planets. As you may know, Jupiter moved inward, Saturn, Uranus and Neptune moved outward and pushed the small bodies out. But not only part of the small bodies around Neptune, they were ejected completely, but part were somehow ejected and came back. So we have actually 3 populations here. The ones which stayed close to Neptune, then we have the cold population which are still in the ecliptic, and we have the hot population in the scattered disk which have some inclination to the ecliptic. That's how they are distributed. You see here the resonant population. They are resonant with Neptune. They are close to Neptune. They have to be resonant to be stable. And then we have this scattered disk here and the extended scattered disk, and Sedna is out here. And at the zoom in, you see the resonant 4 to 3, 3 to 2 and 2 to 1. That depends on the orbit of Neptune. You see the cold population, the classical belt, the cold population, the scattered disk, which are out there and which we can partly see, but partly we just postulate them. So what can we learn from the Kuiper belt? The protoplanetary disk was probably cut off at 40 AU. Nothing more outside. The Neptune is responsible just for the rest. It pushes the small bodies out, it kicks them out, it kicks them fully out. So it's all Neptune's work. And probably distant star encounters also play some role. But the Kuiper belt is much further away from the stars than the Oort cloud. So the role is less pronounced. When Kuiper belt objects come in, they cannot do it like Oort cloud comets just in one go. They will migrate in slowly and become centaurs. Centaurs are small bodies between Jupiter and Neptune. And their orbits are generally unstable because they are just too close to the big planets. They will not stay here for long, just million years, a few million years at most. But during that time, of course, they are already relatively close to the sun, so they will no longer have the 10K, but probably 50K or something like that as temperature. And so far so good. You have the Oort cloud comets, you have the Kuiper or Jupiter family comets, they are called, but it's not that easy. You really can mix them easily. You can convert the Oort cloud comet into a Jupiter family comet, you can convert the Centaur into an Oort cloud, and so on. So in the end, when we look at comets, we know it's an Oort cloud, or it's a Jupiter family comet, we know it from their orbits, but we don't know their original place of origin. It's somewhere between Saturn and outside of Neptune. So, but anyhow, whatever happened, these are leftovers from the earliest time, and most of them were really never very hot. But it does not mean that all comets are from the same place in the solar system. If we study the composition of comets, what we hope to find is traces of all stages of their formation. So we start with the interstellar medium, that's leftover material from dead stars. Then we go to molecular clouds, where we see cloud chemistry, to star-forming regions. Again, a different chemistry than here, into the protoplanetary disk, finally to the solar system, and to the evolution of life. The composition of comets is a mix of all that. And this is given by the starting conditions, with what do you start, by the chemistry, which happens here and here and here, and the physical conditions, density, temperature, ionizing radiation, and time. In the next slides, I will talk mostly about results from Rosetta, because the comet we encountered with Rosetta is the best researched comet. We have most data from this comet because we were there. We followed the comet for 2 years, and we were close to the comet. That's the Rosetta mission launch 20 years ago, almost exactly, 2nd of March 2004. In August 2014, 10 years later, we were at the comet. We needed this time to get on the orbit of the comet. Comets are relatively have a high energy in their orbit because they are eccentric. And we needed 3 Earth flybys and 1 Mars flyby to get to this energy. But then in March 2014, we saw here the first pixel on the camera of the comet. So the comet was exactly 1 pixel. In June, you see it starts to get 2-dimensional at least. And then in July, we found out that it's a weird comet. And in August, we were close to the comet, well, 100 kilometers from the comet, but on the same velocity as the comet. And from then on, we could really follow this comet. We had trajectories, I will come to that, around the comet all the time. That's here, it's hard to see, but it's a selfie. I always claim the first selfie was of Rosetta, and in the background was Mars, 2007 in February. And the iPhone came on the market in July 2007. So Rosetta invented the selfies. So that's the next selfie here with the comet in the background, taken by the camera on the lander. Then we put the lander onto the comet, more or less successful. It jumped a little bit around, but that's okay. Here we were very close to the comet. You see the shadow of Rosetta on the comet, which is not very often that you see the shadow of a spacecraft on a body. And that's during perihelion. You see the comet is active all around. And finally, in September 2016, we ran out of fuel. We went away from the sun. We were again at 4 AU almost, and we had to end the mission. We soft crashed on the comet with Rosetta. That was the end. No more data after that. So, the comet Churyumov-Gerasimenko, or 67P, which is easier. It's a Jupiter family comet, that's clear. It's just 4 kilometers, that's the longest distance. In the other dimension, it's 2 kilometers. It has a rotation period when we arrived of 12.4 hours, but when we crashed, it was down to 12 hours. So it got faster due to outgassing, non-gravitational forces. An orbital period of 6.5 years. So it was in the vicinity of the Earth again last year, fortunately. Perihelion distance inside of Mars, but not inside of the Earth. It has a rotation axis which is tilted, which means it's like on the Earth. You have spring and summer and fall and winter. That plays a big role here. It's, you know, it looks a little bit like a duck, and this duck would actually swim on a lake because the density is less than water here. And it's very porous. 75% of the comet is nothing. And it's black. So it looks like a duck, but actually it's 2 comets which gently collided at one time. And you can find this out from the layering here. Here and here, they don't have the same gravitational center. And from this you can deduce that it's actually 2 comets. And it has a north and a south hemisphere. The north, as you see, it's covered by fine dust. And the south here doesn't have this fine dust. It's actually, it's also not rock. It's sintered material, ice and dust. And I come back to that. These were the orbits we made around the comet. You know, it has so little gravity that you can do everything you want. You can go forth and back or around or whatever. If you are close enough, it's a bound orbit, but most of the time it was an unbound orbit. And that means you see not one place on the comet. You have very different view directions. Sometimes you're over the north, sometimes you're over the south. That's Rosetta. And these are the most important instruments. That's Hermes, Cosima, the dust mass spectrometer. And then we have DFMS, that's a gas mass spectrometer. And we have COPS, which gives you the total density and the ram pressure. And from this you can deduce the velocity of the gas. Let's start with dust. Dust we have in all sizes, starting at 4 kilometers, which is the comet. But then 100 meters, these circular things here are a little bit more than 100 meters. Then 2 meters, if you go towards the ground. 10 centimeters, that's from the lander. You see the leg of the lander, that's 10 centimeters, about. And then that's Cosima. Cosima had targets which were exposed to the coma of the comet, to the comet. You got dust on these targets, and after some time they put them inward and under the microscope, and that's how it looks like. And if you look closer, you see rubble piles. So this dust is really not the rock, it's fine dust. And finally, the atomic force microscope, you see, goes down to 500 nanometers, and still you see structures. So these are probably the very original dust grains from the interstellar medium. Cosima was a mass spectrometer which shot indium ions onto the dust. And you see, these are 1, 2, 3, 4 dust grains. They look very different. Sometimes you have dust grains which are solid, but most of the time you have dust grains looking like rubber piles, and they really shatter around. Also, the velocity was not very high of the impact. And sometimes they shatter only upon an analysis, just by the electric fields of the instrument. If you look at the composition by atomic numbers, 30, 30, 30, hydrogen, carbon and oxygen, equally distributed, and the rest is a little bit here, 10%. If you look by weight, of course, then hydrogen is much less. You have mostly oxygen and carbon. So it's not minerals, or not only minerals. And they could split it up into organics, carbon with heteroatoms, and minerals about half-half. So the dust of the comet is not just a mineral grain, it's a carbonaceous grain. Looking at the elemental abundances with respect to Ci chondrites and iron, these are the 3 comets where we do have data. You see they scatter somehow. And for 67P and Halley, we have much more of the light ones. They were probably lost in the wild grains, because wild grains, they had a high impact velocity, and the volatiles, the organics, were probably mainly lost, so you have less carbon, nitrogen and oxygen here. But otherwise, it more or less resembles a chondrite, except the volatiles. For me, I was the PI of the Rosina instrument, so the mass spectrometer DFMS and the pressure sensor. And then we had a second mass spectrometer RTOF. And so for me, the key is the volatiles, but I know I am biased. Sorry, Hervé. I know that the dust is also very, very interesting, but for me, it's the volatiles. And we have many, many results, and I cannot talk about everything today. So I will talk about isotopes, mainly about the D over H, deuterium to hydrogen, and the xenon. And then I will talk a little bit about the highly volatiles, molecules which are more volatile than CO2. The organics, where we have a real zoo of organics, and finally the salts we found in the comet. Rosina DFMS is a classical mass spectrometer. For those of you who have ever worked with mass spectrometers, it's something which you don't use anymore in the lab, because we have more modern instruments. But I can tell you it's the best instrument ever flown, and even in the last 20 years, nothing similar has gone up. You see the mass range is up to 180 Daltons. We work with electron impact ionization, so it's very classical. But we have a resolution of 3000 at the 1% level, which corresponds to 9000 at the full width half max. That's not very much for a lab instrument, but it's a lot for space instruments. They have normally 1 mass unit resolution, plus minus Cosima is better, but still, you had a mass resolution of about 1,000? Yes. And we have 9,000, so that's the difference. But it's also more difficult to analyze dust and gas. So that's mass 60. You see we have many contributions to mass 60. If you have a mass resolution of just 1, you see 1 peak. And then it gets really difficult. We had very different densities. That's COPS, the density, the absolute density of the gas. You see here we are over the summer hemisphere. This up and downs, that's the rotation of the comet you see, because once you look at the broadside of the duck and then at the rear duck and then at the head. So that makes this up and downs. And here we are over the winter hemisphere where it's much colder and less gas is ejected. You have here CO2 and H2O, which are the main ices in the comet. They all go up towards perihelion and then down again, but you see already here CO2 behaves differently from water. And we have some measurements here early in the mission which shows this clearly. It's the position, the view we have of the comet. If it rotates, here you have little water, then here you have more water than CO2, and then we are again here where you have less water than CO2. So that changes depending on from which angle you look at the comet. That's now for the whole mission. It's before the first equinox, during perihelion passage, and after the second equinox. And that's the latitude here and the longitude of the comet. You see water before the first equinox really came from the north. That was the summer hemisphere at that time. Then during perihelion, the sun moved to the south. So that was the summer hemisphere, and water followed the sun. And then after the equinox, it went back with the sun. It's, the sun here is just north of the equator. Here it was a lot north, about 50 degrees, but here it's just north of the equator. CO2, always in the south, even if the northern hemisphere is in summer. CO, it's a little bit distributed between the two. During perihelion, everything is coming from the south, and O2 follows water pretty well. Now let's look at some isotopes, mostly D over H in water. D over H gives you a hint about the formation temperature of the molecule. The colder, the more you can enhance the D over H in water. Depends a little bit here if you do ion-molecule reactions or molecule-molecule reactions, but in both cases, the colder you are, the more D over H you have. So the protosolar nebula is down here. The local interstellar cloud even lower. And then we have the Earth, which is at 1.5 times 10 to the minus 4. And comet water, which is clearly above the terrestrial water. In the sun, as I said, 1.5 times 10 to minus 5. The Earth 10 times more. Molecular clouds, much more. Here the range is big. And in 67P, we have time times 10 to the minus 4. That means more than 3 times more than on Earth. And from this, you can just follow that the terrestrial water cannot be from comets. Well, it's only one comet, but I will show you that this is true for most comets. So our water has nothing to do, or very little to do, with comets. Even more interesting is the doubly deuterated water, D2O, where both hydrogens are replaced by a deuterium. In molecular clouds, you have 1.2% for this ratio. We have 1.8 plus minus 0.9, so we are in accordance with molecular clouds. And that tells you that probably the cometary water is a product of these molecular clouds, where it's cold enough to enhance the D. The ratio doubly deuterated to singly deuterated versus singly deuterated to normal water should be, statistically speaking, in thermal equilibrium 1/4. In our case, it's 17. So it's highly non-equilibrium chemistry. As I said, we are high for water in 67P, but that's true for almost all of the Oort cloud comets, also probably for WIL 2, only hardly 2. There we are sure that we have a more or less terrestrial value. And now we come back to where were comets formed. They were formed in a broad range in the solar system, and probably hardly 2 was formed further in than 67P, had some isotopic exchange reactions in the water, got water vapor from the cloud, and that's why it's much slower than the others. But if you take the mean, you will end up with 3 times 10 to minus 4, which is not compatible with our water, because the Earth has lost light water, not heavy water. The value on the Earth was higher than it is, lower than it is now. Sorry. We can also look at other molecules which have an H, and in all cases, comets are enriched in the D over H, which means it's not equilibrium chemistry playing a role here. If you have D2O in the gas phase and you have H2O, you will have exchange reactions of isotopes, and you lower this compared to HTO. So this means at least some of the cometary water was preserved as ice and never in the gas phase. Isotopes of xenon, you have this morning heard about nucleosynthesis. Xenon is a very interesting atom because it has many isotopes, stable ones, and each isotope you can tell where it comes from. So supernova is the light ones, 124, 126. Then HEB stars is the middle ones mostly. Here you have an addition of the decay of iodine 129. This goes to 129 xenon. And then we have the R process, which is due to neutron star mergers. There is a paradox on Earth for the xenon. If you normalize everything to the sun here, and you look at chondrites, then you have an increase here, neon, argon, krypton, xenon. That's mass-dependent fractionation. The heavier, the less you lose it with time. The Earth is okay for the first 3, up to krypton, but then it misses xenon in the atmosphere. If we look at the isotopes in the Earth, you have this peak here due to the decay of iodine, but otherwise you have this curve here, which again shows you mass-dependent fractionation. If you correct for this mass-dependent fractionation, you get this here. So we miss in the Earth's atmosphere 134 and 136 xenon. And that was a long-standing question, more than 40 years, I think, until we measured 67P. We could measure the isotopes of xenon in 67P, and now we come to the conclusion. If you take meteoritic xenon from the Earth's interior and you mix it with xenon from the comet, 22%, then you end up in a perfect fit to our atmosphere. Or with other words, we can tell you how many comets impacted the Earth to bring this 22%. For this, you have to assume how much xenon the Earth has lost from the atmosphere. That's a little bit the guesswork. That's the present day xenon. That's the initial xenon. We have somewhere between 17 and 27% from 67P. And that gives you, if you look how much water was brought with the xenon, between 0.05 to 2% of the terrestrial water. So maybe we have some cometary water in our oceans, but very little. That's okay. The Earth is a very dry planet, only 1 per mil of surface water. By comets you have maybe 10 to the 19 kilograms, if you assume 1%, and that gives you organics of 10 to the 17 kilograms. And that's more than today's biomass. That's substantial. The water is not important, but the organics. Let's look at the highly volatile molecules before we go to the organics. Highly volatiles are these here, and a few others. The comet is a Kuiper belt comet, scattered disk comet, so he came into the interior of the solar system via Centaur stage. And in the Centaur stage, these are models, they can get quite warm. So these are 3 different models here. But you see in a depth of a few meters, you can easily reach something like 75 Kelvin in the comet. Of course, the comet, each time it comes, it loses the first few meters. So this goes away, and we may end up around 60 K or so for the comet, where the material sublimates. These are diurnal temperature variations. The comet gets very hot at the surface, 250 degrees, and then cold at night, but that extends only to about 5 centimeters because it's so porous, the thermal Wärmeleitung is very small. The thermal inertia is very high. So there are experiments when you freeze out gas at 10 K and then warm it up, how the gas will come out. And this was done by Cucci a long time ago. We have here more or less cometary abundances, more or less. And what you see, you get peaks for CO and CH4, the highly volatiles, at their own sublimation temperature. That means if you freeze out a mixture of gas, some of the gas will go into a pure phase, not be mixed with the others. Then we have peaks when CO2 comes out. You still have CO, a CO and the CH4 peak here. And you have more coming out, CO and CH4, when water converts from amorphous to crystalline, and then when water desorbs. Now let's see how it looks in our comet if we assume that the gas has been frozen out at low temperatures. If we look just at water and CO2 over the whole mission, that's CO2, that's water, you see the correlation over the whole mission is rather bad. We start here with the dark colors, go towards perihelion, and then back away from the sun, and that's the end of the mission. And there is some correlation because of the heliocentric distance, but not really a correlation between CO2 and water. And that's what I have shown you before. Water always follows the sun, CO2 always comes from the south. This cannot give you a good correlation. Now let's look at the highly volatiles, in this case CO. CO versus CO2, that's here. Correlation not terribly bad, but also not terribly good. With water, CO with water, yeah, we have a problem here at the end of the mission, definitely. But if we do a linear combination of CO2 and water, we get an almost perfect fit. If we say that the pure phase is no longer there, and that's clearly possible because of the central stage, that we have already lost the pure phase. And from this here we get 70% of CO desorbed with water, 30% with CO2. That means part of it is trapped in CO2, part of it is trapped in water. That's also true for methane. Perfect correlation here for this linear combination. Here it's about 50-50, 50% of the methane goes with water, 50% with CO2, which means much more is in CO2 because there is less CO2 than water. O2, you already see it here, the correlation with water is already very good and the combination is not much better. O2 goes completely with water. Don't ask me why. And what's the possible consequence here? If we look at laboratory experiments, then we see that 68% of CH4 is in a pure phase if you freeze it out. And we have lost this pure phase already. 77% of CO. And, well, of course, these are the ones trapping. And this fact here may then explain why Oort cloud comets and Jupiter family comets show different abundances for CO and CH4 and other highly volatiles. There is a paper by Dello Russo where he put together all the data. You see, if you look at CH4 only and CO, then the ratio between Jupiter family comets and Oort cloud comets, now the inverse, is 2.8, and Oort cloud to Jupiter family for CO is 3.8. But if you consider then this, you're almost there. That means Oort cloud comets, they don't spend time in the Centaur region. They still have these highly volatiles. Jupiter family comets have lost them. And now to the organics. Complex organic molecules, I learned in astrochemistry, are molecules which have one C at least and 5 other atoms, which are not very complex. But that's how astronomers see them. And the one example, of course, is methanol. I'm not a chemist, definitely not. And when we started to detect all kinds of molecules, I never could remember their names or their structures or their smell or whatever, but I know animals. So we associated them to animals. For example, the highly volatiles, butterflies, they always go. The monkeys, the funny animals, the alcohols. The long chains here, and the ring molecules. The beautiful and solitaire, the noble gases. The smelly ones here. The poisonous ones. this cyanogen, it always disappeared when we looked for it, so it's, it's a chameleon. Exotic molecules, these are molecules where I didn't know where to put them. And finally, here, the zebra. In a zoo, you don't have horses. But of course, zebras, they smell of ammonia, of horse. And so ammonia belongs to here, methylamine and ethylamine. They are all in one class. And zebras are eaten by lions. So you make out of methylamine and some of these butterflies, you make the glycine, the amino acid, which we found in comet 67P. So that's the story of this. Meanwhile, we have many more animals. If we do the same correlation plot now with methanol, you see neither with CO2 nor with water, nor with a combination thereof, you get the correlation. Methanol, I don't know, it's not in the ice. It must be associated to the dust, probably. Otherwise, you would have a correlation here, at least with water. Our instrument is good enough so that we can separate the pure hydrocarbons from the one with a heteroatom or with N or S or whatever. And if you can do that, then you can put such a plot up. These are pure hydrocarbons up to C10. These are hydrocarbons with oxygen, with nitrogen, with sulfur, with nitrogen and oxygen, and with sulfur and oxygen. So you can separate them. That doesn't tell you which molecule you have. Because we use electron impact ionization, we fragment the molecules. So we get some parent ions, but we get a lot of the rest. But the mean sum formula is this here of the comet. So as I said, we use electron impact ionization. That means we split the molecules. That's what we measured. And then we put in ethane. Ethane, the parent ion is here on 30. So we cannot have more ethane than what you have on 30. Otherwise we would have a conflict. That gives us fragment from 24 to 29, apart from this here. So that does not explain our data. We add propane. The parent is here. We cannot have more propane than that. But we have some fragments here. And then we put up a few other molecules. Still no good. We take all the alkanes we know. Alkanes are singly bonded CC. Yeah, it's better, especially here, but it's a log scale. You don't see it too well, but here we have a real problem. Then we add alkenes double bonded and alkenes triply bonded. Still, that's not yet the solution. So we have to go to cycloalkanes, alkenes, and aromatics. And with this, we can more or less explain all our data for the pure hydrocarbons, only pure, without heteroatoms. You see, that's a mess, first of all. It's not a unique solution, that's also clear. You have isomers, which can give you similar results, but it shows you how complex the organics are in a comet, in a very primitive body, remember. We did the same for the O-bearing, and here I want to point out furan. Furan, that's the molecule we found. Furan, that's this here, the C4H4O. But you see, we also have the dihydrofuran. That's where one double bond is missing, but you have two hydrogens more. And that's more than the pure furan. And the tetrahydrofuran, that's even more. So if you have no double bonds, you have a higher abundance. That means these molecules are well hydrated. And if you have furan with a side chain, that's also more abundant than the pure furan. We are currently working on the nitrogen bearing, and there it's actually the same. The hydrated are generally more abundant than the aromatic, and if they have a side chain, they are more abundant than the just pure ones. And you see that, for example, pyrrolidine with a methyl group is 5 times higher than pure pyrrolidine. So our organics, that's the composition of our organics. We have everything. We have chains with double bonds, triple bonds, cyclic molecules, hydrated or non-hydrated. We have aromatic up to a naphthalene. And these are actually the building blocks of this insoluble organic matter, which they see with Cosima. So I think from the volatiles to the dust, it's a continuum. We can measure up to 140. We have a mode to 180. We still have a signal there. We have not yet evaluated it. But I'm sure there are molecules up to the macromolecules, if you look carefully. But they are no longer volatile, so we don't see them. And they are too volatile for Cosima because they disappear before they are actually analyzed. If we look at the average composition, you see C1 H 1.5, Cosima has H 1.0. That means our molecules are more hydrated than in the dust, which probably makes sense, and they are more Cosima is more hydrated than in a chondrite. So that's more primitive than this here, I would say. Oxygen, they see more oxygen than we see. That could be the mineral contribution to oxygen, also here. Nitrogen, we see more nitrogen than this here, and similar. And, no, they have the same amount of nitrogen, we have a little bit more. And that brings me to the last topic, yes. That's salts. Salts, and I'm not talking about salts you are using in the kitchen, I'm talking about ammonium salts, NH4X. And this forms easily from NH3, which is the base, and AX, which is the acid. They just form. If they encounter each other, they form. And they have a higher sublimation temperature than the pure acid and base here. Upon sublimation, they dissociate back into their original molecules, not only, but mostly. We had a few times during the mission when we had special events. That's H2S versus NH3. And you see, and that's the heliocentric distance, the days here, you see there is not really a correlation between the two, H2S and NH3. You even see these latitudinal effects here. It goes up and down, and it's several orders of magnitude, this ratio. But we had times when we saw such things. Here it's S over O2, because they both have mass 32. If we do this ratio, we can eliminate all artifacts of the instrument, NH3 to OH, the same. And you see, you get peaks, sharp peaks. Several measurement points. One measurement point uses about 40 minutes because we scan through the mass spectrum. And they always fall together, the H2S and the NH3. And it's not only these two, but actually it's many. And we associate that with dust impact. When we have a dust grain directly hitting our gas mass spectrometer, entering the ion source, you get a peak, you release everything which is volatile from this dust grain. And so that's before the impact. After the impact, everything was higher here, even water. But if we normalize to water, you see in the normal coma the numbers and in the impact material. So the most abundant material in the impact is actually ammonia, followed by H2S, and then we have a few others which increase by factors of 100 or more. These are all acids here. If we sum up the abundance of the acids, we get this number here. That's the base, and you see it almost balances. So it's really the salt which we see. The salt of NH3 with all these acids. And this probably explains the deficit in nitrogen we see in comets. That's the elemental abundance in the sun. In comets you see oxygen. Comets have all the oxygen like the sun, carbon, but there is a deficit in nitrogen. But if you assume that a lot of nitrogen is in the salts, and the salt is not released until the comet gets very, very close to the sun, 0.3 AU or so, and we know that NH3 goes up if the comet goes closer to the sun, then you push this upward almost to the solar value. So the hydrogen is just hidden in the salts. So Rosetta clearly contains ingredients for life on Earth. The glycine, I haven't talked about, that's an old result almost. We have phosphorus in a form which is available for life. It's phosphorus monoxide. And ESO made a nice movie about that. Yes, we still have a little bit of time. Phosphorus is formed in massive supernovas and then reacts first pH3 and then reacts to PO and PN. And in the comet we actually find the PO. And with the number of impacts I have shown you from the xenon, we actually did bring phosphorus via comets on the Earth. And ammonium salts, we know these are precursor molecules for urea, nucleotides, amino acids, and others, prebiotic molecules. So these are all ingredients which are at least good for life. Now, it's one comet. Is it representative of all comets? There are some work on that. HCN, you see, and methanol. Methanol has a bigger spread than HCN, but still it's a factor 10. And there is no difference between NA, that these are Oort cloud comets, and Jupiter family comets. They mix. That's a Halley type comet up here. Looking at other molecules. That's CO2. It's more abundant in the Oort cloud, but that's just because you see them at much further distances, where you don't see the Jupiter family comets because they are too weak. But here it's more or less the same. The same for CH4 and CO. I have shown you the factor 2. And then all the others, there is no real trend from Oort cloud comets and Jupiter family comets, which is in my mind not expected because we don't know where they formed. So it's just by chance where they ended up, not where they formed. And it's probably, if you look at these numbers here for these molecules, it's not so far from what we see in dense clouds, low mass protostars, a little bit less in massive protostars. So it's interstellar chemistry what we have in a comet, mostly. So my working hypothesis is water and CO2 are the main ices. Highly volatiles are embedded into CO2 and water. Jupiter family comets have experienced probably temperatures up to 60 K in the central stage, which explains the difference. And complex organics and salt are not part of the ice, but part of the dust. We have COMs up to C10, at least. The rest I have told you already. So, looking at comets, what you see is traces from the interstellar medium. Especially if you look at xenon, you see the nucleosynthesis part. We also have a non-solar silicon isotopic ratio. If you look at sulfur, I haven't talked about sulfur, but you look at chemistry in the dark clouds. D2O star-forming region chemistry, then the highly volatiles, you look at protoplanetary freeze-out of ices. And finally, the ORH in water tells you something about the solar system, the Earth, and noble gases and organics about life on Earth, maybe. There is no proof, but at least it's a way of thinking. So the mixing in the protosolar nebula was probably not very efficient. Prebiotic molecules are rich in comets and may have contributed to life. And that's the end. Thank you.